So today our look at functions will be on inverse functions. So question would be, what does it mean for two functions to be the inverse of each other? Well, let's take a look at this. And if we have a function g, and if it is the inverse of another function we'll call f, then here's what's going to happen. If we have a point letters are not working today. Say AB in function f, then that point will be point BA in G. And we'll switch each other around. We use a notation that would look like this. If G is the inverse, then G would equal F, and then we put a little negative sign up here to look like that. I'll make a note to you to be careful, because we have seen something like this before. And with the exponent in between the f and the brackets here, that's inverse. When it's outside, it's talking about the reciprocal, where we took that f of x and just put it in the denominator. Okay. So make a note to yourself that this is not equal to this. Okay? There are two different meanings for them. Okay. So let's try this out and see how this works out, with the first example being decide if these two functions f and g are inverses of each other based only upon the set of points that we have here. Okay? So let's just kind of read off this table. You can see in this table, if I put in 0 in the f function, I'm going to get 4 out. Okay? 0 gives us 4, so we have the point 0, comma 4. I'm just going to continue across this and look at each one of these points. That would mean that f of 1, we'd go to the f, or the 1 column and the f row, and that gives us 1, so that's the point 1, 1, and continue that all the way across. 2 gives us 3, the point 2, 3. 3 would result in 0, so that's the point 3, 0. And then finally, f of 4 would give us 2, so we have the point 4, 2. So, if G is the inverse of f, then we should be able to go through and find in the G function, the G of x should be, based upon our definition above, we should have the point 4, comma 0, the point 1, 1, which isn't really it might not look like we're doing the inverse of it, but since those are both the same numbers, but 3, 2, 0, 3, and 2, 4 should all coexist there. Yeah. So what we can do is just go through our table, and this time we're going to read off the values in the G function. Okay? And we're going to ignore all of these numbers in the f function. The second row will be ignored, and we'll look at the bottom row of this. Okay? So we'll just start out here And you guys tell me, what do we get when we substitute in 4? What do we get in the g function? Let's start us out.
For 4, it would be 0.
Yeah, we go over to 4 and we get 0. And that checks out perfectly, doesn't it? And then let's check g of 1. Okay, what do we get when we put in 1 in the g function? 1. Go to the 1 column, go down to the g row, and we get 1. That checks out. We're 2 for 2. And then, Colin, what about the next one? G of 3, what does that give us? 3 gives us 2. Check. Looking good. Bella, what about G of 0? 0 gives us 3. We wanted 0, 3. Then Keithan, finish this up. What does G of 2 give us?
4.
Gives us 4. Based upon only these points, we would say that yes, g of x is the inverse. Let's take a look at our next one. So, first of all, I'm just going to list, in this case, the 5 points that will result from the f of x function. Just list those out. Okay. So, we can see at x equals -10 in our f function. Oops. We get 0. I'm just going to read off each one of these and write these down so I have a record of them. And I can quickly switch them around. -5, 10, 0, -5, 5, -10, and finally 10, 5. Then I'm going to take each one of those and just flip them around. This is what would be in the g of x function. The inverse here would be 0, -10, 10, 5, or -5, -5, 0, -10, 5, and then finally 5, 10. Yeah. And then we're going to check this out. In whatever order you want to do it, I like to just start each point 1 point at a time and substitute in the 0 into the g function. That's this column here where we get a -10. Boom. Checks out perfectly. So, Aaron, what about when we have 10 substituted in our g of x function? What do we get? Is that good? Perfect. Check, check. Then, Ethan, what about our next one there?
We get 0.
We get, yeah, I put the wrong one in there. -5 gives us 0. Looks like we're on a roll. And then, what about our next one when we substitute in -10? What do we get? 10, 10. Oops. Does that look good? Houston, we have a problem, don't we? Okay. So, check that again. 5 gave us -10 in the f of x. So -10, 5 should be what we're looking for. But we don't get that. We get -10, +10. Okay, so I don't need to check any more points here. As soon as I got one exception, then I'm going to say no. And again, I checked my work just to make sure. But no, g of x is not the inverse. Let's take a look at inverses when we graph those. We've looked at them from a table point of view. Let's look at them from a graph. Okay? So, if I have any point, and well, it says plot the points of f of x and g of x from the example up above, and let's see what we get with these. So, fortunately, we listed off our points here, so all I have to do is graph these 5 points from my f of x function. 0 gave us 4, 1, 1, to the right 2, up 3, to the right 3, and stay at 0 on the y-axis, and then finally to the right 4 and up 2. We've got all of those points right there. Yeah. Now, before I graph these points, I want to point out something to you. Okay? When we have an inverse function, that inverse function will act like a reflection across the line y equals x. And if you recall from geometry, we even used this notation. We said xy is mapped to yx. Hey, wait a second there. Isn't that telling us to just flip them around? The y became the x became the y. Just like in our definition of an inverse function, every point AB becomes BA. So I don't know if you realized that when you were writing this notation and doing all those reflections, that you were actually doing an inverse function back in geometry. So I should expect, if I draw the line y equals x, the one that goes through 0, 0, 1, 1, 2, 2, negative 1, negative 1, negative 10, this line right here, y equals x, I should be able to find the inverse of that by just taking those points and reflecting them. And indeed, look at our points here. Our point was 4, 0. That will be the reflection of this point here, 0, 4. 4, 0 is here. It's a perfect reflection across that line from our previous point. Each one of these points that we have listed will follow that. And of course, 0 or 1, 1 and 1, 1 are the same point because they are on the line of reflection. Points on the line of reflection stay on the point of line of reflection. Next, our 2, 3 got reflected to the right 3 up 2. These two guys match up perfectly. Then our point 3, 0 becomes 0, 3. And then finally, our last point is at 2, 4, and that corresponds to the reflection of the point 4, 2. Okay. So any point over here, A, comma B, will be reflected across and land over here at the reflection B, comma A, by reflecting it across the line y equals x. Okay. Let's see what happens when we have one that doesn't follow that pattern. Okay. We had a set of points here. One of them was negative 10, 0. That corresponded to 0, negative 10. Perfect. That looked great. We had the point negative 5, 10. Negative 5, 10 was right up here. When we reflected that across, it went to 10, negative 5, right here. And again, it lines up perfectly with that reflection. We went to 0, negative 5. 0, negative 5 corresponded to negative 5, 0. And again, those line up perfectly. Then we ran into the trouble when we went to the right 5 and down 10. This was that point 5, negative 10. But we didn't end up with that because negative 5 or negative 10 resulted in a point up here at 10. Negative 10, 10. And those are not reflections of each other. If I try and line those up, I won't end up with that line that is perpendicular to our line of reflection and occurs at the midpoint of the line that's between those. Okay? So this is the one that caused us to say not an inverse. So let's draw some inverses, not from given the points, but given the graph of one of them. Okay? So, reminder again, we're going to reflect it across this line right here. Okay? Now, one way of doing that might be to take some patty paper and fold it over, or what we're going to do is just quickly make a t-table of our x and y values and pick some easy points in here. It looks like we have negative 1, 1, and then at x equals 0 we're at 2, and x equals 1 we're at 3. So if we make the inverse of that, we're just going to switch those around again. This will be a 1, negative 1, 2, 0, and 3, 1. So I'm going to go to the right one, down 1. That corresponds to the reflection of this point. And then the point that was on the y-axis is going to go to the x-axis. That's the point 2, 0 now. And then our point 1, 3 becomes 3, 1. We have it looking like this. I think I have enough to do this. I know it has this shape of our snake. So this one should also look like a snake. I'll go ahead and rotate my paper just a little bit so I get a better angle at drawing this. It should go something like this. Okay. And hopefully you notice that both of these graphs have a point in common, and that is the intersection on the line of reflection. Let's do the same thing with this parabola. I want to take this parabola and reflect it across this axis here. Okay. So, let's list a few points here. At 0, we're at 1. At 1, we're to the right 1 and up 2. And at 2, we're up here at 5. If I go on the other side, at negative 1, I'm at 2, and at negative 3, we're at 5. So those are the points on our parabola. Our reflection will also be a parabola, but it's going to be flipped the other direction. And again, different ways of doing this, but I think the easiest way, again, is just flipping them around. All these y's, 1, 2, 5, 2, and 5, result in the corresponding x values being the y, or the output of the inverse function, which are 0, 1, 2, negative 1, and negative 3. And I just have to be careful to plot each one of these correctly. So 1, we're at 0. 2, I'm going to go up 1. 5, I'm going to go up 2. Next point was 2, but this time I'm going to go down 1, and 5, but this time I'm going to go down 3. It should look like this. Okay. So now I'm going to go ahead and line these up. Zip, zip, zip. And there we have it. And I think I wrote down the wrong number here. This should have been a negative 2, and this one should be a negative 2 also. I think that works better for me. Okay. Now, it does ask us here at the end, is the inverse of a function always a function? And then how can we tell? Well, over here, is the inverse, the graph in red, is that a function? Would you guys agree that it's a function? Yeah, we know that this function, the green function, passes our vertical line test. Oops, what about this one over here? Is this one a function? No. This one does not pass our vertical line test. Okay. So, in this case, this one is a function, but in this one, it is not a function. Now, we're going to use something to help us out with this. We know that these did not pass the vertical line test. Okay. But if we're looking at the original function, we can tell from that function whether the inverse is a function by doing something that's called the horizontal line test. Okay? The inverse will be a function if the original function passes what's called the horizontal line test. We learned the vertical line test back in algebra. We're going to do a horizontal line test. In other words, if I draw horizontal lines on the original function, okay, or original relation, original graph, and we have no 2 points on one, or 2 or more points on one horizontal line, then it passes the horizontal line test, and the inverse is a function. Not the original one. We're not talking about that one being a function. The vertical lines test is still going on with that one. Look at the parabola over here. This parabola has many horizontal lines that have 2 points on it, so this does not pass the horizontal line test, so it is not a function. How about that? vertical line test to tell if the function is the relationship, the original graph is a function. The horizontal line test tells us whether the inverse is a function. All right, let's take a look here at a couple more. For the following graphs, is f a function and is the inverse a function? How do you know? And draw f, the inverse, on the graph to verify your answer. Okay? So first of all, should we get a function out of this first one here? Yes or no? If I do the inverse of this one, will I get a function? Mitch?
No.
Why not?
It doesn't pass the horizontal line test.
Very good. If we call this f of x does not pass the horizontal line test. Therefore, the inverse is not a function. Okay. It does say to draw that new one. Okay. And I'll do this one a little bit quicker. I do know I should go through this point, and this point, because those are all on that. And then real quickly, I'm looking at to the right 2, down 3, 2 comma 3 here, or negative 3. So let's go negative 3 and up 2 for that point. And let's just see. Oh, there's one other easy point right here. We're at 0, 1, so we have to go through 1, 0. And I think we've got enough to kind of make a quick little sketch. It should go down, hit that minimum point here, and then it should work its way back up to hit this relative max right there, and then go back down in that direction. So that's kind of a quick one. And as you can see, yes, this one fails the horizontal line test on these points, and if we graphed our inverse, you can see that one fails the vertical line test in this spot. Let's take a look at our next one, this graph here. What do you think, Aaron? Will the inverse be a function here? Yep. And why would you say the inverse will be a function? Because? Okay. Oh, well, it's going to be close. We know we're going to do something like this, but given that slope, we know we're going to go through this point, and this one's rather easy. I'm just going to choose the two intercepts. The x-intercept is over here. That looks like at 6. So that should become our y-intercept at 6. And then the y-intercept of the original one is at 3, 0, 3. So we should go through 3, 0. And it should look something like this. And I think you can easily see that the original function f of x passes the horizontal line test. Horizontal line, oh goodness, doing my vertical line test, getting too easy on those. There are all the horizontal lines. That passes. Therefore, the inverse is a function. And that can be quickly verified by taking our sketch of the inverse, and it passes the vertical line test. All right. So now, what if we want to determine whether they are inverses of each other? Well, we can list out all the points, but that can be pretty tedious, especially if we don't have the table already for us. Okay. So there is an algebraic way of showing this, and that's by using our composites. That is, we can do f of g of x and that should equal g of f of x, and both of those will give us x. If that occurs, if this is true, then we know for sure that f of x and g of x are inverses of each other. Easiest way I can do that is skip this example and just go down here to the practice and think about it. Remember what happens when you squared a number and then you took that and square rooted it? What did you always get? You squared a number and then square rooted it. What happened? Yeah, square 7, 49. Square root of that, back to 7. Okay, square 4, 16. Square root of 16 is 4. Okay, so you always get back to where you were. So this one's easy to show algebraically by saying that if we take f and that's squaring that and look at f of g of x, where g of x is the square root of x, we know that that is going to get us right back to x. If you want to look at it algebraically, we know that x to the 1/2 power is what the square root is. Power to a power multiply, 1/2 times 2 gives us 1, and we get x here. And we'll get the same thing if we switch the insides and the outsides, and we look at the composite function with g being the outside function and f being the inside function. In both of these cases we get back to x. Okay? So these are inverses. Okay? Now this one does have a little bit of a, oh, be careful, because we know from this guy right here that we have a domain that must be met. And that domain is that x has to be greater than or equal to 0. Because let's think about what these two graphs actually look like. The first one, x squared, is what shape? Dana, what shape? It's a parabola. So our f of x function is this parabola. Oops! Does a parabola pass the horizontal line test? No. But we do know that g of x, being the square root of x, is a function. And, Dana, what did we call the square root graph? A fishing pole. Okay? It's only 1/2 of the parabola. So these are inverses only on the domain x is greater than or equal to 0. So we have to ignore this part of that parabola. So this one, yeah, they're inverses, but not totally inverses. I can't put in a negative number into the square root function and get anything out. So all these -1, 1, -2, 4, -3, 9 won't work. Okay? So let's go back up to this example and do a quick little practice on this one. F of x being our outside function, that means everywhere we see x, we're going to substitute in this g of x function. And our g of x function is 1/3 x minus 3. We can distribute that 3 to each term in the g of x function. That's going to be 1/3 times 3, which is 1, times x is x. 3 times -3 is -9. And of course that -9 plus 9 gives us 0, and we get x here. Let's check the other way, with the g of x function now being our outside function, and where we see that x, we'll substitute in the f of x function. The f of x function is, of course, like we saw used in the last one, 3x plus 9. Distribute, 1/3 of 3 is 1, times x is x. 1/3 of 9 is 3. 3 minus 3 is 0. And yes, this proves or shows that these are inverses. Let's do another example down below, starting with the f of x function as the outside function, and our g of x function being the inside function of 1/2 x minus 3. Distribute. 1/2 of 2 is 1, times x is x. 2 times -3 is -6. -6 plus 6 is 0. We get the x. Switch that around, and now take 1/2 of the f of x function and subtract 3 from that. The f of x function is 2x plus 6. When we take half of that, half of the 2x is x, half of the 6 is 3. 3 minus 3 is 0, plus x is x. So we've determined algebraically whether two functions are inverses. Now what if they ask us, if we're given a function, to write the inverse function? So it's all based upon that notation. xy is mapped to y comma x. And what's that telling us to do? Well, it's telling us to switch our x and our y. Then, to write that, all we have to do is then do the algebra to solve for y. So watch what happens here. In this function, we're going to take the x's and the y's and swap them. In other words, this will become not y equals, but x equals 3/4 y minus 9. Now what we're trying to do is get that y by itself. So the first thing we can do is get rid of this 9. This, of course, becomes x plus 9 equals 3/4 y. Let's do this in some small steps here. First of all, let's get rid of that silly denominator here by multiplying by 4 instead of dividing by 4. The result will be 4x plus 36 equals 3y. Now, finally, to get that y by itself, we're going to divide by 3. And that's going to give us a 4/3 x plus 12 equals y. Or if we want to switch it around, y equals 4/3 x plus 12. Those two functions are inverses of each other. Let's do a couple more practices and see what we get here. Okay? So, on our first one, we're going to take this and switch around the x's and y's. Of course, f of x would be the y. We're going to make that x, and where we see x squared, we'll make that y squared minus 9. This one's pretty easy to solve. I can probably do it in one simple step by adding the 9 to both sides. This will leave us with y squared equals x plus 9. To get the y by itself, we would need to square root this, and this would be the square root of x plus 9. Except, I've got to make sure I do a plus and a minus on this. So let's think about what this would have looked like. Our original function, this x squared minus 9, is just a parabola that got shifted down 9. That is our f of x function. It's pretty easy to see that this does not pass our horizontal line test. Okay. It has several horizontal lines that are crossing 2 points. Therefore, this is not going to be a function. And just to prove that, let's think about what this looks like if we were to graph that function. Of course, this is going to be a fishing pole. And remember how the inside, when we did a function, inside moves us left and right to get our new 0. And negative 9 plus 9 would give us 0, so it got shifted to the left 9. And the positive side of this is this fishing pole. But this negative is this one down here, which of course does not pass the vertical line test. So yes, we have inverses of each other, but they're not necessarily a function. Let's do our next one. Just take each one of these and switch them around. This will become x equals negative 5y plus 10. I'm going to go ahead and just add the 5y to both sides and subtract x from both sides. Leave us with this. Divide everything by 5, and we get negative 1/5 x plus 2. And there we have it. This one ends up being a function, and if we wanted to, we could write it like this. The inverse of g is equal to negative 1/5 x plus 2. Let's take a look at the next one. This will be not y equals x cubed, but x equals y cubed. If we know to solve for y, we're going to take the cube root of x. Based upon that, we know that h prime of x would equal the cube root of x. And yes, these are both functions, because we know the first one is our snake, and the result is what looks like one of our lazy snakes. Okay. And that's the one that, if you recall, looked like this, our lazy snake. They have, on the line y equals x, 3 points in common. 0, 0, 1, 1, and negative 1, negative 1. Okay. So let's take a look at a typical question you might see on the end-of-course exam or on our test. It might give us a graph of a function, and it's going to say, use the graph of this function, f, and answer these below. First of all, is the inverse a function? Yes or no? Ariam, yes or no? And why? Perfect. Yes. We can look at a quick little boop, 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 boop. And yes, indeed, the inverse of x is a function, and we can say since f of x, not f prime of x, or the inverse of x, passes the horizontal line test. Okay. Now, of course, if you graph the function, or graph this inverse, and checked it, it would pass the vertical line test. And then it does something like this. It says, hey, let's find this. Okay? Now here's the key. When you see this, this is the inverse. So this is saying if we go into the f of x function, the result will be 5. We want to know what this value here is. In other words, be careful. This is not x in f of x. So, in other words, we're not going to go over here to x equals 5 and find this. What we're going to do is we're going to go to y equals 5 and work our way backwards to find out what x equals. So when you see the notation like this, this is the inverse function. And you can see the result is 4. If we put 4 into our original function, we'll get out 5. Therefore, the result is this. Okay. So, what if we do this one? This is saying, what's the result of these two? Okay, so if I go down here to -3, then f of, oops, sorry about that. If I'm looking for this first one, I want to know what I get on the original function, and that is 0. That's what the x is here. So I just did this inside part of this, which means on the outside I'm going to substitute in this 0. And what do I end up getting out? I get out negative 3. Okay. Now, got a little warning here. Stop. Wait a second. Should I be doing a bunch of work here? No, I should not. Because think about this. If I put in any number in the inverse function and put that result back into the original function, shouldn't I end up right back where I was before? Yeah, because think about it. We said we had a point A, B, that then became B, A. But of course, if we put B, A back into that inverse function, won't that switch it back around and get B, A? Okay? So again, when you see anything that looks like this, when they're given f of the inverse of x, doesn't matter what that x is, you're going to end up with x. And they could do it the other way around. Just like I could square before I square rooted or square root before I square. It doesn't matter the order of these. And it doesn't matter what this number is. You're always going to end up with that same number. Even if it's 3.7960432. Don't even have to enter that in my calculator. I'm going to get the exact same number. Let's do a quick little application on this one. It says the distance d in feet that a car is required to come to a complete stop while traveling r miles per hour is given by this function. Write a function to express the rate r at which a car is traveling as a function of the distance required to complete the stop. And then are these inverses and not. Okay? So, again, what it's telling us is, hey, you're going this fast, this is how far it's going to take you to stop. Okay? Well, what if I just wanted to go the other way around? What if I wanted to know, hey, I'm this far away, what should my speed be in order for me to stop? Okay? At that distance. So I might use the function the other way. Rather than be given the rate and find the distance, what if I know the distance and want to know the rate? Okay? And you can kind of think about that. Yeah, you're doing maybe that stunt in the movie, and you want that car to stop exactly 1 inch away from the person and get that great effect. Okay? So, all right, how far do I have to start braking before so that I don't hit this person? Okay? So, what we're going to do is we're going to take this function here, and remember, we just take and switch things around. Okay? And the result will be, again, this is d equals 6.97r minus 90.39. And if we switch that around, then this will be r equals 6.97d minus 90.39. Are these inverses of each other? Okay, well, again, let's solve this one. Actually, yeah, I think I don't want to do this. I just want to solve this one for r. I don't want to switch those around because r is always going to be r. I just had a little mental breakdown there. And this one, d equals 6.97r minus 90.39. What I want to do here is just solve for r. Okay. So if I add 90.39 to both sides. I'll have 6.97 times r. And then r will equal d minus 90.39, all of this divided by 6.97. And that's what I could put in my calculator to solve for that. Now, we've got two quick ones down here, just to reiterate some of the typical questions you might also see from this. And the first one is, if f of 3 gives us -1, what would be the inverse of -1? Just want to make sure you see, yes, it is that obvious. If we look at the original function we put in 3 and we got out -1. So this one being the inverse function, this -1 that goes in here should give us 3. And then we already went over this one. If these two are inverses of each other, then if we put 17 in the inverse function, then put that back in, of course, we'll get right back to 17. Okay. Wonderful. You guys did well. Good job.